we are solving systems of equations using matrix factorization, specifically LU factorization and PLU factorization. They're very similar, slightly different. So before we get into what the heck matrix factorization is, we need to understand what an elementary matrix is. So an elementary matrix, called E, that's our notation, is found by performing exactly one row operation on the identity matrix. So if I take identity, here's an identity for a 3x3, and I perform a row operation on it. So one of my row operations would be, okay, so R2 equals, 4R2. Then my elementary matrix would look like this, where I multiply row 2 by 4. If I swap two rows, so if I said row 1 swapped with row 3, my elementary matrix would look like this. And if I did my elimination step where I said row 3 equals row 3 minus 2 row 2, it would look something like this. Row 3 is going to be 0 minus 0, 0 minus 2, and 1 minus 0. So these are my three different versions of an elementary matrix, and it depends on which row operation you use, but essentially we get these patterns where if we multiply a row by a constant, then that row is just multiplied equals that number. If I swap rows, then it's just identity out of order. And if I do the elimination step, then I end up with what is called an elimination matrix. So an elimination matrix is an elementary matrix obtained using row operation 3. I do want to point out when we talk about elimination, we are talking about strictly row operation 3. Row operation 3 is defined as a row equals a row plus some multiple of another row in order to do that elimination step to get that 0. The row we are using can be multiplied by anything. So this number here can be any constant, does not matter. But the row we are replacing cannot be multiplied by anything. So this coefficient here needs to be 1, otherwise it's not row operation 3. It's a combination of constant multiple and elimination. So when we're talking about using just elimination, just row operation 3, it has to follow this form, where it's a row, we are replacing it by adding it to some multiple of another row. We cannot multiply the row we're replacing by a constant. So when I do that, let me just remove this elimination matrix down. So note I got this elimination matrix here by doing this row operation. And you'll notice my elimination matrix has an extra element. It has an extra non-zero entry called a multiplier that occurs in the ij position, corresponding to the multiplier value that I use in my elimination step. When I say the ij position, the I corresponds to the row we replaced. The j corresponds to the row that we used. So over here, we replaced row 3, and we used row 2. So this multiplier here is L3, 2, because we replaced row 3 using row 2. And note, it shows up in row 3, column 2. So for these elimination matrices, for these elementary matrices, it turns out that if we multiply a matrix by one of these one of these elementary matrices, it appears to do the row operation for us. So if I take this matrix times A, it's going to do this row operation on A. It's going to multiply row 2 by 4. If I multiply this one by A, it's going to go ahead and swap rows 1 and rows 3. If I multiply this one by A, it's going to go ahead and take row 3 and subtract 2 times row 2. So when we multiply EIJ, so when we multiply our elementary matrices, our elimination matrices, by a matrix, then it appears to actually do that row operation for us. Which this is really powerful because in MATLAB, in programming, in algorithmic design, If we can do something with just a basic matrix multiplication, it means things can go faster. Okay, last thing to note before we actually get to our matrix factorization method is when I do the inverse of an elimination matrix of an elementary matrix, specifically an elimination matrix, I get the same matrix. So let's call this E32, because I replaced row 3 using row 2. E32 inverse looks exactly the same, except the sign on that multiplier changes. So now instead of it being -2, it's +2. And that's important later on. Okay, so now that we have that foundation, let's go ahead and look at how we do or why we even want to do matrix factorization. Just to note, when we say matrix factorization, it just means we're taking A and breaking up into a product of two matrices. One's called L, one called U. So if matrix A can be reduced to a strict upper triangle matrix, reduced means we can do our elimination steps. When we get to REF using Gauss elimination, we are reducing the matrix. So if it can be reduced to a strict upper triangle matrix, that's essentially REF, that's our strict upper triangle matrix, using only elimination, only row operation 3, only Rn equals Rn plus some multiple of Rm. Then it is possible to represent the reduction process, those elimination steps, in terms of a matrix factorization, in terms of a product of two matrices, where the first one is called L, and the second one is called U, where L is a lower triangle matrix with my upper triangle of zeros, and U is an upper triangle matrix with my lower triangle of zeros. So, what we're going to do for a 3x3 matrix, 2, 1, 7, 9, 4, 3, 6, 1, 8. For a 3x3 matrix, in order to get it into REF, I need to make this a 0, this a 0, and this a 0. I need to do 3 elimination steps to make my 3 zeros. When I do an elimination step, it appears as if I am multiplying my A matrix here by an elimination matrix, like I set up here. If I take E32 times A, it's going to perform this row operation. Oops. This row operation. So, since I need 3 elimination steps, I can represent those 3 elimination steps as 3 elimination matrices. And we will call them E32, E31, and E21. Where E21 is to make this one a 0, 2, 1. This one is E31 to make that one a 0. And this one, 3, 2, to make that one a 0. Which means that REF can be represented as A times 3 elimination matrices, times 3 elimination steps. So here is U. That's REF. How I can get to REF. Using 3 elimination steps represented by 3 elimination matrices. The L matrix then ends up being the inverses of these 3 matrices. The inverse of E21, the inverse of E31, and the inverse of E32. And the reason for that is because if we want to go ahead and solve for A here, so U equals E32, E31, E21 times A. If I want to solve for A, I'm essentially going to multiply by the inverses. So I'm going to multiply it by E32 inverse, which gets rid of that one, E31 inverse, which gets rid of that one, and E21 inverse, which gets rid of that one. I'm multiplying both sides by those inverses, but as you know, with matrices, order matters. So it's E32 inverse, E31 inverse, and E21 inverse. So I'm doing this, multiplying both sides by my inverses. So these all cancel each other out, and A equals U times all of this, which is out. And we will look at an example of how this plays out in class. So if I want to go ahead and find LU, L times U for a given A matrix, here's what I'm going to do. Solve for row echelon form. Find REF. by using only row operation 3. Only elimination. Here's my 3 row operations. Do not change these. It's always these row operations. I'm going to replace row 2 by adding it to some multiple of row 1. That gets me this 0 here. I'm going to replace row 3 by adding it to some multiple of row 1. Gets me this 0 here. And then I'm going to replace row 3 by adding it to some multiple of row 2 to give me that 0 here. That's going to give me 3 row operations. These values here are my multipliers. These are the ones that show up in my elimination matrix. They show up here. The last thing I'm going to do is I'm going to go ahead and change the sign on those multipliers and plug them into L, where L looks like this. L21, negative L21, negative L31, and negative L32. This becomes my L. And there's my U in REF. So essentially, we're doing Gauss elimination, except we're doing it with the same 3 row operations every single time. Okay, so don't get creative, don't get crafty. These are your 3 row operations all the time. There's another way to do LU factorization. We'll just call it method 2. Essentially, what you would do is you know that L is going to look like this. I'll write it out. Where L looks like this, and U looks like this. U11, U12, U13, U22, U23, U33. Where you would do the multiplication with these coefficients in there, with these numbers in there, or with these variables, is what I meant to say. And you end up with this matrix here. And you solve for U11, U12, U13, and all of the values one at a time by setting these matrices equal. So A11 is always U11, A12 is always U12, A13 is always U13, and then A21 is this, where you already know what U11 looks like, so you can solve for L21. And you just work your way through. Essentially, you have 9 equations, 9 unknowns, and you solve for them one at a time. I do want to point out that I need to do better when it comes to the negative sign on L21, because here, the negative sign is not included. Here it is included. So keep that in mind in terms of what you're doing. Okay, so once we have our LU factorization, once A equals LU, then the whole point of this is to solve systems of equations. So here's what it looks like. If A equals LU, then AX equals B can be broken down into LUX equals B, where this is A. Then what we end up with is 2 mini systems of equations, where LY equals B. So here we have a middle step, where we're going to add in some middle unknown, y, and say Ly equals B, where L looks like this. Note I didn't include the negatives there. And then y is some unknown, and then B comes from our system of equations, where we can easily solve for y using what we call forward substitution, where we get our first unknown, that gives me my second unknown, gives me my third unknown, as opposed to back substitution. Once we know y, then here we can say ux equals y, where u looks like this. And then x is our unknown in our system, and then y is pulled down directly from here. Then we get our last unknown, solve for our second unknown, solve for our third unknown, so that's our normal back substitution. And there we go. We've solved these system equations using LU factorization. Okay, so that works well for a decent amount. But what if A looks like this? My first row operation for LU factorization is R2 equals R2 plus some multiple of row 1. Note, there's a 0 here. there's a 0 there. If you end up with a 0, then you need to do some sort of row swapping. But LU factorization does not account for that. It's saying don't get fancy, don't get crafty, don't do any row swaps, just do those 3 row operations. But if we end up with this situation, LU factorization breaks down. So that's where we have PLU factorization, where P means we're also going to include row swaps. P stands for a permutation matrix, which is the name of an elementary matrix that is obtained using row swapping. So row operation 1. So row 1 swapped with row 3. That's really it. Same idea. If we multiply A times P, it's going to go ahead and appear to do the row operation just like we did when it was EIJ times A. Does that row operation. Same thing. If we multiply the permutation matrix, the elementary matrix using row swapping by A, it appears to do the row swapping for us. So PLU factorization is going to allow us to do those row swaps. It's called pivoting. And partial pivoting means that we are going to use our permutation matrices to first ensure that the largest magnitude entry in the column to get our zeros is going to be in the pivot location to perform our elimination steps. So here's what we do. To solve for REF, we're first going to do row swapping. So if I look at that matrix that I had up there, we're going to first look at column 1. In column 1, we're going to identify the number with the largest magnitude. So I would say this is my largest magnitude. Then I would go ahead and swap that to put that 6 in the pivot location for column 1. So I would swap rows 1 and rows 3. Now I have my largest value in the pivot location, and I can do my row operations. I can do row 2 equals row 2 plus a multiple of row 1, row 3 equals row 3 plus a multiple of row 1. Then I would end up with something. I don't know what it's going to end up with. I guess I could do it. This would be 0, so row 3 is good. Row 1 will not change. And then this would be -2. So 3, nope. It would be 1/2. When you do LU factorization and when you do PLU factorization, you end up with lots more fractions just because of the nature of the method, the fact that you cannot get creative, you cannot get fancy. But I would end up with something like 0, 4 minus 7 halves. Oh, good lord. 4 minus 7 halves. 1/2. 5 minus 8 halves of 1. Something along those lines. Okay? Once that happens, don't check my math. Once that happens, then we're going to go ahead and now look at column 2. And in column 2, ignoring column or row 1, this now doesn't appear. We're going to go ahead and do the same thing. We're going to look at our numbers there, and we're going to do row swapping in order to make sure the largest magnitude is in the pivot location. So the largest magnitude between these two numbers is 1, so I would go ahead and swap rows 1 and rows 2. After I do that, then I would do my elimination steps for that column, and I would keep working forward. So at this step here, when I do my row swapping, I end up with a permutation matrix that's going to head and do that row swapping. So my permutation matrix that does this would be the same as I did here, swapping rows 1 and rows 3. So this is the permutation matrix that would do this operation. So P times my A here. I'll move things. P times A does this row operation. This is what it looks like. Same thing here. Same thing down here. If I did this row operation, it would appear as if I multiplied it by this P, where rows 2 and rows 3 were swapped. So here's P1, my first row swap, here's P2. In order to find my overall P, I would just multiply those together. The inverse of those is exactly the same, there's no change, so it's just P1 times P2. Then I would go ahead and put my L matrix together, Putting L together is a little bit more complicated than just plugging in the values to this matrix. It's a little bit more complicated, and we will go over examples of how to do it in class. But essentially, we work our way backwards, following the row operations as we go up in order to put together L. Once we have PLU, then I can go ahead and I can solve my system of equations. So PA equals PLU. That's essentially what I did, which means PAX equals PB. So if I swapped my columns or my rows in A, I swap them in B as well. So we end up with PLU equals PB. And then it's just the same. We still have our middleman step with this Y here. But we say PLY equals PB. Once we have Y, then we can go ahead and solve for X by saying UX equals Y, similar to what we did with LU factorization. And like I said, we will go over many examples in class, talking through how to do this. Note, it is the same steps every single time. You do not get creative with LU and PLU factorization. The same steps. And it's essentially just Gauss elimination. It's just Gauss elimination in an algorithmic exact way, where it's always these row operations. It's always these row operations right here. For PLU, same thing. It's always these row operations right here. The rest of it is just putting the matrices together and solving our system using this middleman, and then solving it with UX equals Y, where these are much easier systems to solve compared to using substitution.